Mendelian inheritance and risk assessment. This actually comes from the pre-matriculation material, but we're going to go over it more now. So inside of every cell in our body, we have chromosomes, and on the chromosomes are genes, and genes are like scaffolds that hold genetic information. We have 23 chromosomes, 2 sets of each, and each chromosome, the genes are considered alleles, so there's 2 copies of each alleles except for the sex chromosomes. So what's a genotype versus the phenotype? The genotype is the identity of an allele or person for a particular locus, and the phenotype is the exhibited outcome. So the genotype is based on the genetics that you have, and the phenotype is based on both the genotype and the environment. Dominant disorders, you only need 1 copy of a non-functional allele to exhibit that phenotype. Recessive disorders are far more common, and both copies of the allele at that site need to be non-functional before you exhibit the phenotype. And so that's the most common form of inheritance. Whereas if you carry 1 copy that's not functioning, that's a heterozygous carrier. So let's go to determine recurrence risk. The determining of the inheritance risk for a disorder, when in doubt, draw it out. So here we have an animation. If mom and dad are both carriers for a big A and a little a, then when we do our little Punnett square, there's a 1/4 chance that mom and dad both give the big A allele. Dad could give the big A, mom can give the little a, mom could give the big A, and dad could give the little a, or both parents could give the little a. So here are all the different possibilities. So there's a 1 in 4 chance that both parents, if they're carriers of a particular recessive disorder, will give the non-functional allele. So what about calculating? And again, I don't know how much you're going to be asked to calculate this, but we're going to talk about the common things for calculation of Hardy-Weinberg, and I may come back to this for other inherited disorders, just to pound it home. So p squared plus 2pq plus q squared equals 1. This is a mathematical formula used to determine the relationship between the allele frequency and the genotype frequency. It's most often used to determine the frequency of heterozygous or carriers for a recessive disorder, but it can have other uses. So let's say we have 2 alleles, A and B. So we could have 2 A's, we could have A and B, or 2 B's. And this is just showing a jar with a bunch of these jumbled around, and so you pick 2. And the genotypes are distributed in proportion to the frequency of the individual alleles in the population. And they remain constant from generation to generation. So if the allele A has a frequency of little p, and B has a frequency of little q, p plus q equals 1. In a population, AA is p squared, AB is p plus q plus p, or 2pq, and BB is q squared. So p squared plus 2pq equals q squared, or p squared plus 2pq plus q squared equals 1. Now, there are a lot of assumptions of the Hardy-Weinberg law that are impossible to meet, but nevertheless, the assumption is there's no mutation occurring at the locus. There's no selection for or against any particular genotype. And the population is large and randomly mating, and there's no migration in and out of the population. If all of these assumptions are met, you're at equilibrium. If the population is at equilibrium, changes to the allele frequency will average out in the next generation. Again, in reality, this doesn't really happen because of consanguinity, assortative mating, and a lot of other things. But this is what we use for assumptions when doing the calculation. So if allele 1 is p and allele 2 is q, p plus q equals 1, p squared plus 2pq plus q squared equals 1, Q squared is the recessive disorder in an autosomal recessive disorder. So if disease X has a frequency in the population of 1 in 100, then Q squared is 0.01, or Q is 1, P is 0.1, P plus 0.1 is 1, or P is 0.9. So the carrier frequency would be 2 times 0.9 times 0.1, which would be 0.18. I show you this, and yet from now on, I'm going to tell you almost nothing has a frequency of 1 in 100 in the population. Most things are 1 in 1,000 or less, and so we're just going to consider P to be 1. So you can figure out Q squared and then assume P is 1. So let's talk about autosomal dominant disorders. In autosomal dominant disorders, unaffected homozygotes is P squared, affected heterozygotes is 2PQ, and affected homozygous is Q squared. This is so low, you can ignore this. In dominant disorders, what we're really looking for is 2PQ. So if they give you the population risk of something, then they're giving you Q, and we're trying to figure 2PQ. Whereas in a recessive, if they give you the population of the disorder, they're giving you Q squared, and then we can figure out the carrier frequency based on the Q squared. So let's talk about an autosomal recessive disorder, phenylketonuria, or PKU, which we're going to learn about in the next section. But this is a metabolic disorder. It's a super rare autosomal recessive disorder. I could call it anything I want. It doesn't matter as long as I tell you it's recessive. And the frequency of PKU in Ireland is 1 in 4,500. So what is that? I just gave you what Q squared is. If all disease-causing alleles are grouped and treated as a single allele with a frequency of Q, then the frequency of affected individuals, Q squared, is 1 in 4,500, and Q is 0.015. Again, we're going to assume, I just showed you that one example to show you how you calculate P, but let's just assume P is always 1, and for your situation, I will never give you anything that P is not 1. So just say, okay, just calculated Q, 0.015, and P is 1. So 2PQ is, let's put this P in here, 2 times 1 times 0.015, or about 3%. What about dominant disorders? Huntington's chorea is a neurologic disorder that occurs in 1 in 10,000. And again, I could call it disease, X is autosomal dominant, and the population is 1 in 10,000. So the name doesn't matter. What is the frequency of Huntington's disease? Or what is the frequency of Huntington's disease allele? Well, if affected individuals are 2PQ, which is 1 in 10,000, then if we assume that P is 1, because 1 in 10,000 is 0.9999, so 2 times 1 times Q equals 1 in 10,000, because we told you 2PQ is 1 in 10,000. So what is Q? It's a half of 10,000, which is 1 in 2,000. And it doesn't matter what disease we're talking about. If they say disease whatever, it doesn't matter anything about that disease. Just think, okay, is it recessive or dominant? If they're giving you Q squared, if it's dominant, we want to figure out 2PQ. And if it's recessive, we want to figure out, if they're asking me the carrier frequency, 2PQ. So it depends, A, what they ask you, and B, what they're asking for. So there's lots of, if they gave you Q and they said, what's the population risk, you'd figure out Q squared. If they give you 2PQ and they ask you what the population risk is, and you're figuring out Q. Autosomal dominant disorders, when we look at a family history, we see it in many generations. We see both males and females that have inherited this, and one of the keys to dominant is that you have male-to-male transmission. Even if there's tons of males in the family and you're like, oh, is it X-linked? Just look for that. Recessive, often the first individual in the family, there are a lot of carriers before somebody is affected because both parents have to be a carrier for the same disorder. Now that gets us to, how does that happen? Well, sometimes we know and sometimes we don't. The carrier frequency for sickle cell anemia is 1 in 10 in the African American population, which is a really high number. Some people believe, well, actually, it's pretty well believed that sickle cell being a carrier, or 2PQ, increases your chance of survival with malaria. So that's why this gene is higher in the African American population, because in Africa malaria killed people. But if you're a carrier and you survive, you're going to pass on your genes to the next population, the next generation. Whereas cystic fibrosis is 1 in 65 in individuals of African American descent, but in the Caucasian population it's 1 in 29. Ashkenazi Jewish means you're Jewish and you came from Europe, and they were a very small inbred population, and that can increase the risk of certain recessive diseases in individuals of Ashkenazi Jewish descent, have an increased risk of a lysosomal storage disease known as Gaucher's, again, cystic fibrosis, Tay-Sachs, and dysautonomia, as well as Canavan's disease, which is another metabolic disorder. And individuals of Asian descent are higher at alpha and beta thalassemia. We also see Tay-Sachs in the French population, in the French Cajun population. So, and then beta thalassemia is higher in the Mediterraneans. But everybody has what's their higher risk or lower risk. So a Caucasian woman is pregnant. Her spouse has a brother with cystic fibrosis. The husband is not affected with cystic fibrosis. What is the risk they will have a baby affected with cystic fibrosis? So, it doesn't matter if I use CF or any other recessive disease. What does it mean for his brother to be affected? That means both of his parents are carriers, okay? So if you have an affected child, both of the parents are carriers. So if mom and dad, let's make our Punnett square. The brother either got 2 good alleles, a good from mom, bad from dad, a good from dad, bad from mom, or both non-functional, but he didn't get this because he's not affected, so we can take this out. So there's only 3 possibilities left, and 2 of these 3 is that he's a carrier. So someone who has a sibling with a recessive disorder is at a 2/3 risk of having that disorder. So the chance that the father is a carrier is 2/3. The chance that the mother is a carrier, actually using that graph on the other, is 1 in 29, which is population risk. If we go back here, we'll just use the, for 1 in 29. What's the chance that they both give the bad allele? Well, let's go back to our Punnett square on the opposite thing. What if they both give AA? There's 4 possibilities. There's 1 in 4 chance that they both give the non-functional copy. So 2/3 that dad's a carrier times 1 in 29, population risk for mom. No family history, but she's Caucasian, 1 in 29. And what's the chance that they both give the bad gene? 1 in 4. And again, I can be talking about cystic fibrosis. I can be talking about any recessive disorder. If I give a pedigree that a sibling is affected, this individual's at 2/3 chance because they don't have it. And this is the same question they're going to ask you, whether they call it cystic fibrosis or disease X or whatever they ask you. So, in conclusion, autosomal recessive disorders are the most common inheritance. Hardy-Weinberg allows us to calculate recurrence risk, and the incidence of a disorder in the population needs to be calculated.